Vanakkam. Welcome to this course on biomedical instrumentation. We have been looking at biopotential electrodes and some principles concerning biopotential electrodes. We looked at half cell potential, we looked at impedance. In this video, we looked at another dimension of or another design consideration for a biopotential electrode. Whether it is a measuring electrode or a stimulating electrode. You are wondering, oh, there are two types. Yes, those that stimulate, for example, those that are used in a pacemaker are stimulating electrodes, whereas those that measure ECG are recording electrodes. Fundamental difference between the two, materials and principles, everything change. We will discuss that in detail. By the end of this course, you will be a master of these topics if you follow the course and the syllabus and read on top of what is taught. If you read up and also take the exam and the assignment seriously, you will master all this. I also learned this, so you can also learn. So, we all can learn. So, in this class, we focus on polarization. What is polarization? When current flows through the electrode electrolyte interface. So, here is a metallic particle, here is the electrode particle and there is an electrolyte interface. When current flows through this electrode electrolyte interface, polarization happens. Usually, technically speaking, this should not happen in an ideal electrode, but it normally happens. Almost always there will be a polarization that will happen, causing and the electrode potential to change from the standard equilibrium potential, equilibrium value that is measured. This change is due to polarization that happens. This change is called as over potential. This is the difference between the actual non-zero current, potential at non-zero current and potential that is there when the current is 0. How is this possible? Current is 0, but potential is there, because there are other effects that are causing this current, or there are other effects that are causing this potential. 0 current potential is called as the over potential. It turns out that over potential itself can be classified into 3 types. One is called as ohmic over potential. This is essentially due to the resistance of the electrolyte. This is due to the resistance offered by the electrolyte. This essentially, if I take 2 points within the electrolyte and measure the voltage drop between these 2 points in the electrolyte, what you measure is essentially the ohmic over potential. This is the voltage drop along the path of conduction. Right? This is similar to Ohm's law. It is essentially proportional to the current. More the current, more will be the potential drop. Another is the concentration gradient or the concentration over potential. In this case, note within the ohmic over potential, I can minimize by having high electrolyte concentration. Concentration will minimize VR. To reduce VR, I can have a high electrolyte concentration, but there are only so many cases when I can do that. This is not always possible. The other is the over potential that is caused due to concentration. In this case, when there is a depletion of ions or accumulation that is happening near the electrode electrolyte interface, there is a change in the concentration gradient that happens locally near the electrode electrolyte interface, not far away, not everywhere. So, local changes that is happening that limits the amount of diffusion that can happen. Right? This occurs in dynamic environments where diffusion cannot really keep up with ion flux. So, it essentially provides a limitation, provides a barrier to the flow of current. The other is the activation over potential. This is due to reactions that happen when charge is being transferred. This is due to charge transfer reactions. So, there is an energy barrier that the ions will have to cross that they will have to overcome to either enter or leave the electrode interface, electrode-electrolyte interface or surface. This energy barrier is due to activation. Right. This happens at low values, low over potentials and at small currents. I mean, consider for example, I mean how do I visualize this? Let us say I am looking at a busy restaurant, it is a busy restaurant, and how quickly can you have your meal in that busy restaurant depends on multiple dimensions, but I could classify this into say at least 3 big differences. One is the size of the entry door, that is the ohmic over potential. Essentially is there, it is a constant, it is there. The size of the entry door limits how fast you can enter the room, enter the restaurant, and that is a constant, that is not going to change. Second is availability or non-availability of ingredients, that is the concentration over potential. How much of an ingredient I have, how much of something I have, how much concentration of something I have depends on is the availability or non-availability of ingredients. Third is how fast can you make a dish, that is a process barrier, that is not dependent on what materials you have the ingredients, but depending on what item is being ordered, the time taken to deliver that food item might vary, which is a barrier that is coming due to the process itself, that is a process barrier, that is the activation over potential. Comparable. I mean, there are other things that come into the restaurant example, I am just giving a rough overview. Remember, these are only examples, these only work so far, the parallelism works only for so long, they will not work wherever you want. Okay, so you will have to limit. Again, this picture I have essentially I have adapted, modulated, changed from Webster, the standard textbook. So, the total potential over potential is essentially the sum of these 3, the 0 over potential VO plus the 0 current over potential EO plus the 3 over potentials, or the 0 current potentials EO plus the ohmic over potential plus the concentration over potential plus the activation over potential. Now, let us look at an example numerical. A metal electrode shows the following potentials. At equilibrium E naught is 210 millivolts, and when stimulated it is showing an potential of 285 millivolts. Okay. At 0 current it is 210 millivolts. At stimulation it is showing 285 millivolts. If the ohmic over potential is 30 millivolts and the activation over potential is 25 millivolts, somehow they have measured this, do not ask me how. Okay, for the purpose of this problem, somehow I know that the ohmic over potential is 30 millivolts and the activation over potential is 25 millivolts. The question is, what is the concentration over potential? That is the question. Well, let us go back to the previous slide that says Vp is E naught plus Vr plus Vc plus Va, is it not? The Vp is E naught plus Vr plus Vc plus Va. The question is, what is Vc in this? What is Vp? Vp is the potential that is measured during stimulation, that is 285 is E naught 210 plus what is the ohmic over potential Vr? Vr is 30 plus Vc is what I do not know, plus Vc plus Va is 25 millivolts, so many millivolts. So, that means Vc is 285 minus 210 minus 30 minus 25. What would that be? 285 minus 210 is 75, and if I subtract 55 from 75, I essentially end up with 20 millivolts. This is the concentration over potential in this case. Now, the other case, critical distinction is the distinction between perfectly polarizable electrodes and perfectly non-polarizable electrodes. Perfectly means nearly perfectly for a practical case. In a perfectly polarizable electrode, no actual charge crosses the electrode-electrolyte interface. So, then what is the current? The current that crosses the electrode-electrolyte interface is only a displacement current, as you would see in an ideal capacitor. So, the electrode essentially behaves like a capacitor. This is the platinum electrode. This is the example of a platinum electrode. platinum electrode is an electrode whose properties approach that of the nearly perfectly polarizable electrode. So, for example, in this case, if I have resistance to be infinity in this equivalent circuit of an ideally polarizable electrode, if resistance is infinity, then all current will flow through this. That current will be a displacement current, essentially a capacitor. That is what happens in a platinum electrode, right. No actual charge crosses, only a displacement current happens. Whereas in a perfectly non-polarizable electrodes, where the current passes through the electrolyte interface without any energy drop, any extra energy, without requiring no energy to make the transition. This is a perfectly non-polarizable electrodes. That means that they have no other overpotentials. There is no ohmic overpotential, there is no concentration or whatever activation overpotentials. Essentially behaves like a short circuit. In this case, there is a capacitor, but the resistance is 0. I mean, not short circuit per se. Later we will look at silver chloride electrode and its design, where I will say that silver chloride must be present at some quantities to make sure that it is not a short circuit, because otherwise it is as good as connecting silver lead to the body surface. It is not like that. Silver chloride needs to be present. So, it almost behaves like a short circuit is the correct way of saying that. Resistance is approaching 0, but not exactly 0. Okay. So, almost they behave as a short circuit means what? Behave as a short circuit? Well, almost behave like a short circuit. The typical example of a nearly perfectly polarizable electrode is the standard silver chloride electrode. Note that the application will determine which one of these electrodes you will use. For example, if you are interested in a stimulating electrode as that of a pacemaker or in deep brain stimulation or other such cases, you prefer polarizable electrodes such as the platinum electrode. Whereas if you are interested in recording, for example, an ECG, then you prefer a non-polarizable electrode. So, the application determines which electrode to use and what is the particular design to adapt. Okay. So, with this we come to the end of this video. In this video, we looked at one critical design constraint or design characteristic, or one critical characteristic, defining characteristic of an electrode, that is polarization. With this, we end this video. Thank you very much for your attention.